the first section of the EDP and the Applied Mathematics Seminar. Today, we are pleased to introduce two great mathematicians, the Professor Wolfgang Arendt and the Professor Karl Kunisch. Para introduzir the Professor Wolfgang, we invite the Professor Laurent Prové of UERJ, Universidade Estado of Rio de Janeiro, and the Professor Karl will be made by Diego from Universidade de Sevilla. Please, Professor Laurent, to introduce the Professor Wolfgang. Thank you.
Well, thank you. Well, thank you, Professor Mauro, for your nice introduction. Well, it's a huge pleasure to introduce Professor Wolfgang Arendt today. He's a professor at the Institute of Applied Analysis at the University of Ulm in Germany. He has more than 8,000 citations and H-index 39 as well. His area of expertise in partial differential equations covered topics related with elliptic equations, singular theory, mathematical physics, analytical and numerical methods as well. And his talk is entitled, When Does the Galerkin Approximation Converge? A Characterization and Application to Finite Elements. So, Professor Wolfgang, you can start.
Well, many thanks for the nice introduction and many thanks for the invitation. Well, actually, I'm very much also a functional analyst, and I'm only a little bit a numerical analyst. And this talk today is on numerical analysis, but I mean, numerical analysis is also analysis just with other aims. And I will talk. My talk is based on a German-French cooperation and on this paper, Galerkin Approximation for Linear Problems in Hilbert and Banach spaces. Let me start with the Lax-Milgrom theorem, of course, which everybody knows. V is a real separable Hilbert space during the entire talk. And we consider a bilinear form, which is continuous. And then we want to solve the problem, given L, an element in V prime, the dual space, find U such that AUV is equal to LV for all V in V. Okay, so this is a problem P, and this will occur again and again in this talk. Now, if the form is coercive, so this means AUU absolute value is larger or equal to alpha U, the norm of U in V square, then the Lax-Milgrom theorem says there is exactly one solution. And I want to use in this talk the word well-posed for saying that there's exactly one unique solution. I mean, that the inverse is continuous, this is automatic in all these cases. So well-posed will be just existence and uniqueness. So this is the Lax-Milgrom theorem. To have a concrete equation in mind, let's take omega, an open bounded set, and we look at the Poisson equation. So given F in L2, find U in H2 intersection H10 omega such that minus Laplacian U is equal to F. So H1 is the first Sobolev space, and H2 is the second Sobolev space. The Laplacian, well, if we have this regularity of the solution, then the Laplacian is just a is the sum of the second derivatives. And we are looking for directly boundary conditions. So we consider H10 as a closure of the test functions in H1. So this morally, these are the functions vanishing at the boundary. Okay, so this is the Poisson problem. And now we want to treat this with forms. And well, one nice thing for forms is that we have the Lax-Milgram theorem. And in this case, the form is just a classical Dirichlet form. So the classical Dirichlet form, now defined on H10 cross H10, is given by the integral of over omega of gradient u gradient v, or this is just the sum of the integral sum dj u dj v. This is a continuous form, and it's also coercive. This is the Poincaré inequality. The reason for coerciveness is the Poincaré inequality. So by the Lax-Milgram theorem, we have a unique solution of the problem P. And now if omega is convex, then one can prove that U is an H2. And in any case, it solves the equation minus Laplacian U equal to F. The fact that it is H2 is not at all easy. I mean, this is a classical result which is due to Catlet's from 64. Of course, most people cite the book of Griswold, or it's a well-known result important for, well, analysis and also numerical analysis. Here we need the convexity or some regularity of omega. It's also true for omega being C2. Now, my next point is the aim today, our aim today is to look at a perturbed equation. So again, we look at omega open bounded and convex, and we consider coefficients Cj, which are just measurable and bounded. And then the problem, I call it the Poisson equation again, is given f, find u in H10 of omega intersection H2, solving now minus Laplacian plus sum Cj dju plus C0u equal to f. We can replace here the Laplacian by strictly by an elliptic operator of strict order 2 with Lipschitz coefficients. Then all the results are valid. But I think it's easier to understand for the Laplacian just for presentation. Now we have a new form. This is not the classical Dirichlet form. It's a form which is perturbed by integral over omega, the sum of Cj dju f, Cj dju v. So there's a sum missing. Okay. And this form now is not coercive in general. Well, actually, yeah, it is not a coercive form, but still we want now, the problem is we want to solve this problem, and also we want to solve it an approximation. So this is the aim of this talk, and I will give a result at the end. Now, we define an approximate problem. So we consider a sequence of finite dimensional spaces, Vn, each of these, and we assume that for each V in V, so V is in the given Hilbert space, the distance of V to Vn goes to 0 as n goes to infinity. So this is a little b. And the little b, I define the distance. So the distance is the infimum of norm of v minus chi in Vn. So this means, given a v in V, I find a sequence Vn in, or chi-n in Vn, and chi-n converges to V. This is what it means. This is the hypothesis that the distance goes to 0. And this is all. So this we call an approximating sequence. Since our space is separable, such an approximated sequence exists always. So it's very easy to define some approximating sequence. But of course, later we want to consider approximating sequences which are adapted to our Poisson problem. Now, given L in V prime, we have two problems. Well, we have the exact problem. So we look for U in V such that AUV is equal to LV. This is the last problem, the second problem. And this corresponds to our Poisson equation if we take A this special form. But we have also the approximate problems, Pn. So find Un in Vn such that AUN chi is equal to L chi for all chi in Vn. And people call this the discrete problem for, well, because it's finite dimensional, one calls it the discrete problem. So we think that this problem can be solved easily solved by numerical means. And then the question is whether the UN approximate U. This is the question. Now, I mean, if we are in the classical case of a continuous and coercive form, I mean, then things are very nice. There is a lemma due to SEA. So both problems, P and Pn, are well posed. And if U is given L in V prime, U is a solution of P, and UN is a solution of Pn, then we have an estimate. The difference of U minus UN, so the error, the norm of the error, this is the norm in V, is smaller or equal than m over alpha, the distance of U to Vn. This famous lemma by SEA, he proved it in 1964 in his thesis. He was a student of Lyon's. And by the way, I mean, he was professor in Nice. I had him as a professor and followed the course of him. So this lemma has a very easy proof. I mean, just 2 or 3 lines. But it's surprising because you see what it says is, well, whenever we have the solution U, the approximation by the UN which are given by the problem Pn, by the solution of the problem Pn, is just, it converges as fast as it can up to the coefficient m over alpha, because it's smaller than the distance of U to Vn. So it reduces the problem to an interpolation problem. So we have to find good Vn such that, well, the distance goes to 0 fast. I mean, this is what we have to prove, but there are no solutions anymore involved. We just have to study an interpolation problem. The problem, how can we approximate a given function in V by elements from Vn, just elements, not solutions. So this is a surprising, fantastic lemma. Okay, so we have this distance. We have to study this distance, the infimum of U minus chi norm chi in Vn. Okay, now for the classical Poisson equation without the coefficients, things are done already by this lemma. Well, they are not yet done because we have to study this interpolation. But now our problem was, or what we wanted to discuss, to consider, is what is happening if our form is not coercive. I mean, and then there's a condition, well, which is known already, had been studied by people, actually by Brezzi and Babushka. So we call it the BNB condition. So this BNB condition is a condition for the form and also for the approximating sequence. So given are two things, the continuous bilinear form and the approximating sequence. And then we ask that there's a beta larger than 0 such that the supremum of AU chi is of norm in less than 1, and chi is in Vn. This should be larger than beta u, the norm in V, for all u in Vn. So this is a series of inequalities, but this inequality should be true for each n. So this is the point. This inequality is independent of n. That's what we ask. If the form is coercive, one sees right away that this is true. But now we consider this more general condition. Well, how can one find such a condition? I think this is very easy to see. This is a last remark which I make. If we consider this operator an from Vn to Vn prime, which to u associates au as a functional, I mean, then BNB means just this operator is bounded below by beta. And this beta is independent on n. And now you see bounded below, I mean this, well, in infinite dimensions, this means just that the range is closed, so we only have to prove that the range is everything. Okay, so we have this BNB condition. Here's a result. So recall, we look at the exact problem and then the discrete problem. The BNB condition implies uniqueness for the problem Pn. So uniqueness, this is in the remark A, the little remark A written down. It means given a u in Vn, if AU chi is equal to 0 for all chi in Vn, then u is 0. This is uniqueness. Now, since we are in finite dimensions, this is just the same as being well posed, the problem being well posed. To 0 for all k, I mean, then u is 0. This implies BNB. So if we have BNB, then we have uniqueness of the problem Pn, and so Pn is well posed for each n. Now here's the result. Assume that we have BNB for some beta. I mean, then also P is well posed, and this has to be proved. And if we consider now for a given L, the solutions U and the solution UN, then we have the same as in Sear's lemma. I mean, the difference of U minus UN is smaller or equal than M over beta distance U to Vn. Okay, now this is basically a known result. This constant, the same constant as in Sear's lemma, I mean, this is due to Shu and Sikatanov. This is a clever proof. Okay, but the proof of this is a little bit more complicated than just in the Lax-Milgram theorem. And in particular, what is surprising, we get also existence and uniqueness for the problem P. Okay, so BNB implies Galerkin convergence. Now we studied this condition BNP more in detail, and in particular, we proved the converse, which is somehow of surprising. So assume that PNP is well posed for all n, and assume, and now, well, assume very little. Assume just that the discrete solutions are bounded. So for each n, we have a discrete solution un, and I ask that this sequence is bounded. And then this implies already BNB. So this is a very weak assumption of, well, not even convergence, implies already BNB. But then BNB implies a much stronger convergence than, I mean, just this bounders. So even if we have only weak convergence, I mean, then BNB holds, and then it converges, well, as fast as possible. I mean, this is what this says. This inequality, norm u minus un smaller or equal than m over beta distance u to Vn, this says it converges as fast as it can up to this constant m over beta. Okay, so this is BNB. But, I mean, now you see things are a little bit complicated in real life, because you see, for this condition BNB, given was a sequence, an approximating sequence, and then we have to find out whether BNB is true. But the reality is different. Maybe we have a very nice approximating sequence for which we have an interpolation result. And the question is, do we have then BNB? So somehow we want that BNB is fulfilled for any approximating sequence. And this leads to a new notion. And the notion is essentially coercive forms. To understand how one may find this condition, look at coercivity. It's easy to see that coercivity can be reformulated by saying that if un converges to 0 as n goes to infinity, then already the norm of un converges to 0. This is equivalent to coercivity. And now we weaken this condition. We weaken it in the following definition. We say a continuous bilinear form is essentially coercive if, well, two things. We assume that un goes to 0 and un converges weakly to 0, then this implies that the norm goes to 0. So this is weaker than coercive, because in addition, we may assume that un converges weakly to 0. Okay, so this is a definition of essentially coercive. Now, what is this good for? Well, first of all, the Fredholm alternative is true. So assume that we have an essentially coercive bilinear form which satisfies uniqueness. This means AUV equal to 0 for all V in V implies U is equal to 0. Well, then P is well posed. So we get automatically solvability, surjectivity is automatic. From injectivity, we can deduce surjectivity. Okay, so this is one nice thing about these essentially coercive forms. But the true reason is written down on this slide. So this is an important slide. So given is a continuous form, and we assume that P is well posed. So we know by analysis that we have existence and uniqueness for the exact problem. And now the following two things are equivalent. The form is essentially coercive if and only if the following is true. So whenever we have an arbitrary approximating sequence, so just an approximating sequence, then, well, starting with some n0, Pn is well posed. So there exists n0, so for all n larger or equal than n0, Pn is well posed. And now, given L and V prime, and calling the solutions as before U the solution of P and Un the solution of Pn, then the difference has the desired estimate. So the difference is smaller than some constants distance of U to Vn. That's what we want. And we want it for arbitrary approximating sequences, because then we can ask somebody who is good in interpolation to find a good interpolating sequence or approximating sequence, and then we have the estimate. We then we have the estimate for the solutions, for the discrete solutions. They converge as fast as possible. Okay, so this theorem holds. Now, what can we do with this theorem? Now we look at our problem. We look at our problem. We have omega, well, which is convex, say, and bounded open. We have the Cj, which are in L infinity, and we have this form we had already considered before. So besides the classical form, we have these extra terms, sum of Cj, dju integral over, and then C0 the same. And now this form, well, is continuous, this is easy, but it's essentially coercive. And I just tell you why. Why is it essentially coercive? So let un be a sequence going weakly to 0, and such that un goes to 0. Okay, so un goes to 0. And then we have to prove that un. Then we have to prove that un goes to 0 for the norm in H1. Now the reason is because the injection of H10 into L2 is compact. This implies that un goes in norm of L2 to 0. In the norm of L2, it goes to 0. Now we have to show that it goes in the norm of H1 to 0. But these lower order terms, they go all to 0 because Gjn goes weakly to 0 and un goes strongly to 0, so the entire thing goes to 0. And now look back at it. So the second and the third term goes to 0. And now, so since un goes to 0, gradient un, the integral has to go to 0, and this is exactly, this implies that un goes to 0 in H1. So it's easy to prove that this form is essentially coercive. Now, I recall this H2 regularity because this is important. So whenever we have, well, now you see, we assume that the coefficients are such that we have uniqueness. And then we have well-positiveness of the problem. And you see, this is an operator which is compact resolved. So this means just that 0 is not a directly eigenvalue. This is the hypothesis. 0 is not a directly eigenvalue. This is very, there are only discrete eigenvalues going to infinity, and 0 should not be one of them. This is our hypothesis. Okay, then we have a unique solution. And now this Cadlet's result tells us that U is even in H2, and we have, of course, by the closed graph theorem, it's smaller equal than C times F. So remember this Cadlet's result. We have we assume uniqueness, and then we have a unique solution. Okay, now I talk about finite elements. This is a very simple case of finite elements. Well, the finite elements are simple, but the equation is a little bit, it's not a coercive equation, and this is maybe not, this is unusual. Well, this is new. So let's look in dimension 2 at a convex polygon. Convex is important to have Cadlet's result. And now what we do is we look at triangulations. So this is just what the image shows. So we have triangles in omega, open triangles, which are disjoint, but the closure, the union of the closure is the union of omega. So this is a triangulation. Well, there is another condition. But I just put away this condition. This is a technical condition. It should be admissible, but this is, let me. Okay, now interpolation is known for these triangles. And this is a result of Philippe Clément. It's a famous result of Philippe Clément. This paper, which was is a result of his thesis. This has, I don't know, this has 700 or more citations, and everybody knows Clément interpolation. So we consider this the finite element space. So given this triangulation, this is all functions in C omega bar, continuous on C omega bar, which are 0 at the boundary. And on each triangle, it's a affine function. So it's just a plane somewhere in the space. And it's affine on each T-bar. So that's all. Now, the given is a fixed number kappa, a big number. I mean, this is just big. Now, the triangle should not be too flat. So the outer radius divided by the inner radius of each triangle should be smaller or equal than kappa for all T in talk. And this will be for the rest of the talk, we asked this. And then, given H, we look at triangulations such that the larger radius, so the outer radius, is smaller or equal than H. This is the last line with a red ellipse around. So RT is larger than H. And then we have the following result. This is Philippe Clément. There exists C larger than 0 such that the distance of V to my finite element space, Vt, is smaller than a constant, kappa, and then H and the norm of V in H2. So this is a crucial thing. So the nice thing, the H is outside. The H is a factor. And then we have a constant and the kappa, this is a fixed quantum, and then V in H2. Okay, this is Clément interpolation. Now, we define a sequence of finite elements. So given is kappa, fixed, for each H, we look at a TH, a triangulation, satisfying these hypotheses. And then we call these, the VTH, we call VH. So VH is such a finite element space for such a triangulation. And for each H, we have this. So look at the first line. The first line was this finite element space. Now we call it VH because for each H, there is given a triangulation. And since our form is essentially cursive, we get the following. Okay, and this is the final result, nearly the final result. So let F be an L2 and let U be the exact solution. We assume throughout that we have uniqueness. So we have one exact solution. And now our result, which we had formulated before, so I show it to you again. So the abstract result is our form has the universal Galerkin property. So we can take an arbitrary approximating sequence, and then we get the estimate. U minus UN is smaller or equal than gamma distance U of Vn. Okay, so we do this here. So for each H, we look at the solution, the discrete solution, and we call it UH. This is a discrete solution. And then we have this estimate. The norm of UH minus U in H1 is smaller than gamma, the distance of U to VH. So this is the last line in the theorem. And this distance, by the result of Clément, can be estimated by a constant times H times the norm of an L2. And the proof is, you see, this distance is Clément, he says it's smaller than a constant H times the norm U in H2, but by Cutlets, this is smaller than a constant H times the norm of F in L2. So we have a very nice result concerning the approximation of U in the H1 norm. It's linear. It converges linearly because it's smaller than a constant times H for each fixed F. Okay, and now there's a trick which is which is known, and this trick also works for our essentially coercive forms. We even get L2 convergence. The L2 convergence is better than the H1 convergence. It's quadratic. You see, in this last theorem, we have the distance of u and UH is smaller than a constant times h squared. So it converges very fast. Okay, for this we need convexity, of course. And this is my finite result. And I mean, if you want an introduction, maybe you or somebody wants an introduction to finite elements and maybe to PDE on a low level, this book just came out 3 or 4 days ago. And this is a book with my colleague in numerical analysis, Carsten, here in Ulm. Thank you for the attention.
Thank you, Professor Wolfgang. It was a very, very excellent talk. Congratulations for your book. Well, now we have time for questions. Anyone can use your microphones or write something on the chat to make questions.
Yeah.
Anyone?
I have to warn you, my battery is nearly empty. I didn't know that it would go so fast, but it may be interrupted suddenly.
No problem.
You see, this is not on purpose. This is not because the question is too difficult, you see, so.
No problem. No problem, Professor. Anyone with a question? Your microphones are open.
I have a question.
Okay.
Professor, the bilinear form A, it is symmetric. It could be non-symmetric.
Oh yeah. It could be non-symmetric. This is well for it could be non-symmetric. Every result is true. It's not used. Well, the form is not symmetric in our case. If we have the CJ, it's not symmetric.
Yeah. Okay.
I mean, for the last result, the L2 convergence, the quadratic convergence, we need that the adjoint problem has the same properties. I mean, for instance, that Clément, the result of Clément is true also for the adjoint problem, but this is of course true here in this case. Because there's a trick which uses the adjoint form, this Aubin-Nietzsche trick uses the adjoint form, and so. Well, but symmetry is not used at all, otherwise.
Please.
Okay.
Good evening, and thank you very much for your talk. It was very interesting. I would like to ask a question that is the following. You have considered one single problem where the bilinear form and the linear form are fixed, but in practice you need to perform numerical integrations. And that means that you have, in fact, a whole family of, in general, a whole family of bilinear forms, a whole family of linear forms on the right. Then yes. My question is if the result applies to, with an appropriate modification to the practical case in which you have to use numerical integrations.
Okay, so this is a very good question. I mean, of course. Somehow we are working on this subject, and I will remember what you asked. This is a very I don't know in the moment, but this is a very good question. I mean, for this BNB one sees what one needs. You see, I think this is well. Okay, this is a very good question. Probably one needs some assumptions on the AN.
Okay,
thank you very much.
Thank you, Professor Henrique, for your question. Any more questions for the audience? Well, if we don't have any more questions, let's thank Professor Wolfgang again for a very, very excellent talk. And now we have some words from Juan. Thank you, everyone.